All right, so now that we went ahead and derived these equations right here, we can go ahead and start coding this out to go ahead and solve for the temperature of our bar over time. So let's go ahead and hop on over to our notebook here, and let's go ahead and import our computational tool. So we'll import NumPy as NP, and that will just be what we use for our computations. And let's go ahead and think about what we want to code in here first. Well, let's just go ahead and start putting in our variables that are going to be constant for this whole time. So our global variables are going to be, what's contained in this R value. So our heat diffusivity, which is alpha, our delta T, our delta X. So we can just go ahead and let's go code those in. So we can say alpha is going to be equal to, let's say, 1, our time step length. So let's call that delta T. Let's say that's equal to half a second. So every half a second, we're going to take a time step. And we need to do the same for X. So this is going to be establishing how long our segment length is in each bar, or in our bar. So let's say we have segment lengths of, let's say, 1 meter. I think that's a good value. And so what do we need to do with this? Well, we have our length of our segments, our time segment and our segment of bars, but we need to determine how many of these we're going to do. So let's say that the number of time steps we're going to take is, let's say, 2,000 is a good number. That's going to be 1,000 total seconds, since we have 2,000 time steps that are all 1/2 a second. That's going to be a total of 1,000 seconds. And let's go ahead and do the same thing for our segment lengths. And let's say that is, or how many segment lengths. And if we say we have 50 segment lengths of 1 meter, that means we're going to have a bar that is 50 meters long. Obviously, we can change these numbers around, and let's say a real metal, if we're doing this in a real life problem, that's going to have, that material is going to have some heat diffusivity that we're going to need to look up. But for now, we're just going to set these to these arbitrary values. Next thing we can do is, I kind of touched on it already, but we can solve for the temperature, or not the temperature, the total time that we're going to be running this for, as well as the total length of our bar. So we can say that our time is equal to delta T times our number of time steps. So that's the length of each time step multiplied by the number of time steps. And let's go ahead and do the same thing for our X. So we're going to say X, or our bar. So we're going to say X is equal to delta X times the number of segments. And we can go ahead and run this. And let's go ahead and just take a quick peek to make sure we typed everything in here right. So our time is 1,000 seconds, and our bar is 50 meters long. Now, one thing I want to do before we get too far into this is I'm going to go ahead and use our NumPy range for our number of X segments. And now what that's going to do is it's going to break up this X into each segment. So now X is going to be this array of 1 meter segments. And that's going to be useful for later on when we're looking at our entire bar. So the next thing we can do is, now that we have these variables, let's go ahead and look at what we need to solve for next. So with our segment length, our time step length, and our heat diffusivity, we can go ahead and solve for our R value. And then we're going to eventually use that to solve this equation right here. So let's say R is equal to alpha times delta t divided by delta x to the power of 2. And we can go ahead and check that value to make sure it's somewhat reasonable. 0.5, that seems about right. And so with these values, we can go ahead and actually, we can start looking at solving this equation. So let's solve this for when our time is just equal to 0. Actually, I'm getting a little bit ahead of myself. Before we even touch this equation, let's go ahead and set up let's say a virtual bar for what we're going to be solving. So what we can do is we can say the temperature throughout this bar is going to be equal to numpy.full, so we're going to create an array. And we're going to want this array, which is going to be a virtual representation of our bar, to have a certain number of values in it, which is going to correspond to the number of segments we have on our bar. So if we have 50 segments, we're going to want this array to have 50 values. So that is given by an x, and we need to set a value to each one of these segments. And since this is the temperature of that bar, let's go ahead and set each segment to be an initial temperature of, let's go with 20 degrees Celsius, about room temperature. There we go. And so now we should have an array of, 50 values, all set at 20. And one key part of this problem is that we're going to have two ends of this bar are going to be at different temperatures. And then we're going to look at how the heat diffuses into this bar. So let's say the temperature on the left-hand side of the bar, the very first value, let's say that's equal to 50 degrees Celsius. And, nope, sorry. So we're going to say T, we're going to look at our temperature array, and we're going to index at 0, which is our very first value. It's going to be this first segment here, and we're going to say that equals 50 degrees. And then our temperature at the end, so -1, that's going to index the last value, is going to be equal to 80 degrees. Let's just go with that. So on the left-hand side, we have a segment that's at 50 degrees, right-hand side 80 degrees, and in between the rest of the bar is going to be 20. And with this, like I guess it's at our initial state, when time is equal to 0, we can go ahead and plot that out and see this visual representation of what we have. So let's go ahead and actually import our tools that we'll need to plot this. So we'll go import plotly dot subplots, and then we're going to from plotly.subplots, we're going to import make underscore subplots. And then what else we're going to do? We're going to do import plotly.io as PO. And then next we'll want to do po.templates.default. And we're going to want to set this equal to plotly dark. And what I'm doing here is this is just going to be, these last two lines are just to give us a format that looks a little bit more pleasing, make everything look nice and pretty. If we run this, plotly.po.templates. Did I make a typo here? It's just template. Po dot templates. oh, wait, import, that's what I did, messed up. Plotly.io, there we go. That's the part I missed. There we go. So what we're going to go ahead and do is let's go ahead and use those functions we just imported to plot our initial state of this bar. So we'll say that we'll go fig equals make underscore subplots, and we're going to say our subplot's going to go in row 1, and our it's also going to go in column 1. And then we can do a fig dot add underscore scatter, where our x value is going to be equal to x. That's just our segments, so from all 51 meter segments. And then our y is going to be our temperature. So we'll plot temperature in the y-axis. And let's go ahead and name this. We'll call it, let's just call it initial. So if we plot this, we can go ahead and see, move my face a little bit, we have a graph that's representing the temperatures of our bar. So at the very left-hand side, we have a temperature of 50. On the very right-hand side, we have a temperature of 80. And in between, everything is 20 degrees Celsius. So this is at a initial state where time is equal to 0. Now, obviously, this isn't too helpful. And what we'll want to do actually is go ahead and take it a step further and iterate this over our time, which we already defined up here. So we'll want to iterate this equation here over our number of time steps. To do that, we'll go ahead and we'll need some sort of loop. In our case, let's go ahead and use a for loop. So we'll say for I in range. Let's go from 1 to our total number of time steps. So we want to run this loop for our total number of time steps, which is in our case 2,000. So I'll put nt. I'm also going to put a +1 on there, and that's because Python will run this from 1 to our set value, but it won't run it for that last value. So there's our for loop, and let's go ahead and code in our equation right here. We don't need to worry about time when we're coding this in. We're more worried about position because this for loop is going to run it for each time iteration. So what we'll say is time or temperature, our temperature array, and we're going to access it from 1 to -1. And actually, let me explain real quick why we're going from 1 to -1 and not from the very beginning. So let's say that we have, let's say we have our bar, and it goes from 1 to, let's say, 10. It has 10 segments starting at the number 1. If we input 1 into J, here it's all good. So we get 1, 1, 2, 1, but here we get a 0. And 0 is not part of this array, so we would try to be calculating some value or pulling some value that's not there. And the same goes for later on. We won't go take these numbers all the way to the end, because if we do so, we'll get a j plus 1, which would put us 1 past. So we'd get, let's say, j is 10 in our hypothetical situation. Then on this variable, we would get j being 11, which doesn't exist. So we're going to go from 1 to -1. And then later on, so that will allow us to have these j plus 1 and these j minus 1. So that's that position plus and minus 1, be that before and after segment, essentially. So that is going to be equal to 1 to -1. You notice they're at the same position, j and j. And then we're going to add our r value multiplied by our temperature. And here we have that first situation where position is different. So we're going to add 1 to both of these. So we're going to go from position 2 all the way to the very end of our array. And we're going to subtract 2 times our temperature. This is at position J as well. So it's going to go from 1 to -1. I guess I should probably elaborate that in Python, 1 is the second value in an array. So 0 is the very first one, 1 is the second value. That's why we're going with 1. So that's technically not the first value, because I guess that can be confusing sometimes. Anyway, so let's carry on. And then we're going to add our temperature at, here it's going to be J minus 1. So we're going to go from the very beginning of our array to -2. And there we go. So that is, I guess that probably just solved our equation. But what we're going to want to do before that is let's go ahead and create something to plot this information. But there is one issue with plotting all of this information, and that is that we have this going over 2,000 time steps, which 2,000 time steps is a lot of lines to graph. And if we did graph that, it would just be a jumbled mess. So what we can do is let's try to break this up so we plot, every 50 to 100 seconds. Maybe gives us a little bit more of a break here. So to do that, we can say, we can create a conditional statement where we're going to say if I modulus 100 is equal to 0, then we will plot our line. And what this modulus here is doing is it's doing I, whatever the I value is in our for loop, divided by 100, and then it's going to find the remainder. So let's say I is 100. 100 divided by 100 is a 1. There's no remainder, and therefore the output of this function is 0, and we can run our conditional. If I is 33, we divide those, there will be some remainder, and we won't plot that. Anyways, let's go ahead and we're going to just copy this over because it's the same code pretty much. So when this conditional statement is true, we'll go ahead and add a new plot. Let's make this here, and let's change the name F, and then let's go I times delta T. And all this is doing here is making our units as seconds. So this is that'll just be the name on the side. It'll keep it as seconds. So let's go ahead and run this. Oh, actually, there's one thing I'm missing. Let's do fig.show. And if we run this, we'll get an error, I guess. Let's see what the problem is. Mode properties scatter. Is it lines, I believe. So it's the S's. There we go. So we fixed that. And there we go. So here we have our initial. So this is our initial graph. And then we have 50 seconds, so that's 100 time steps. And that's what this modulus is doing, is it's saying I is equal to 100. So 100 time steps is ultimately 50 seconds because we said our time step size is 0.5 seconds. So every 50 seconds, we're getting a new line. And as you can see, as the time progresses and we approach 1,000 seconds, we get a flatter and flatter line. So a closer and closer to this equilibrium between 50 degrees and 80 degrees Celsius. And now let's go ahead and, so we have our graph pretty much. And what we can do is let's go up here and mess with some of our numbers. So let's say our delta t is, let's change that to 1. There we go. So that's going to say our time step is now 1 second. Oh, okay. So that is something that is not very, that's pretty ugly. That is a massive number we're getting over here on the side. And this is not at all what we should be looking at. Let's go ahead and set that back to 0.5. So we set that back. Everything looks normal. Let's go ahead and change something else. Let's make this. Let's say we make this 0.5. And same thing. We were getting something that is not quite looking right. So let's think about, well, maybe, actually, sorry, let's think about this, I guess, in a logical sense, as logical as we can be with this mess. So it's not just us changing the delta t or our delta x, and those aren't used in any further calculations other than calculating our x and t, which shouldn't really have an effect on our graph too much. It's just setting our variables along here, but that, again, shouldn't have an impact on the data we're graphing. The only other calculation that we're using them in is calculating our R value. So it has to be something with our R value. So let's go ahead and see what our R value is right now. So it's 0.5 right now. So let's just go ahead and manually change it. So we'll comment out that line there. And let's say R is equal to 0.5. That's what we had before. Should look the same. There we go. So it looks the same. Let's go ahead and let's make that, let's say, 0.4. There we go. That looks fairly normal as well. Nothing too out of the ordinary. Well, let's go up with it. Let's go to 0.6. And there we go. So that's the error right there. When R is getting too high, we're getting these weird oscillations. So maybe let's drop it back down. Let's change it back to 0.51. Maybe that's so we just kind of want to see at what point is this R value becoming volatile like this. So 0.51 is still too much. Let's try 0.1. Okay, so there we go. That's probably the clearest picture we're going to get of seeing what happens here. So as this R value is getting above 0.5, we're getting these weird oscillations, which are becoming more pronounced the longer this runs for. And actually, it might be a little hard to see along these earlier plots. There is still some oscillation. They still wobble a little bit. But again, it just becomes obviously more and more pronounced the farther we go along this time step. So actually, the reasoning behind this oscillation is going to be what we cover next. So next, we're going to hop on over to the board and look at the von Neumann stability analysis. So I'll see you guys over there, and thanks for watching this part of the video, and I'm just going to go on and hop on over to the whiteboard now.